So as some of you tuned into the talk that I gave last week, some of you may not have, so I'll review a few things. One of the reasons I'm doing this series is all those landslides in December got people a little bit more interested in the geology of Haines than perhaps they were before. So last week was an overview. Tonight I'm going to talk about the rocks of Haines. There's still a lot of different topics that I haven't covered and I'm not going to cover tonight, and I hope next fall to put together a series that talks more about earthquakes and faults and tsunamis and how to identify minerals and rocks and various other things. So keep an eye out for that. So the talk tonight is going to be about an hour long, at least that's my best guess. I only had time to practice this talk once. If you have questions, you can use the little chat feature. You can look on your screen if you haven't done it before, and I can see the chat messages quickly. I may not be able to answer your question during the talk, but go ahead and type it in. I might be able to, or I'll answer it at the end. And I have put my picture on this slide this time because some of you may not know me, and through the year you might have questions about geology, and if you see me, you can stop me on the street and ask me a question. I might not know the answer, but I might. Okay, let me, there we go. Okay, so I'm going to review something I did last week. I talked about the jigsaw puzzle thing, which is, if you think of the geology of an area as a giant jigsaw puzzle, and where the pieces represent clues, they're rocks or other kinds of data, and we put it together to figure out what the geologic history is. So here's a picture. You can imagine that's the puzzle, but the problem is that we're not given the picture, and we're only have maybe 30 pieces out of a 1,000-piece puzzle. And so we have to do our best guess. But because we've done this before, we know that sky pictures go on the top. We see a picture with mountains, so we know the mountains are going to be under that. And we have a piece over here that's got mountains and sky and water, so we know there's water in the picture, and we put the water there. And these ones, you may not be able to tell, but I'm a geologist, so I've done puzzles like this before. These are forest, and from that we can start kind of guessing where the boundaries between those things lie, and then we may guess that the picture looks something like this, and you can see our guesses are approximately right, but they're not very precise and not very accurate, but it's a good sense of the overall picture. We don't have all the pieces because some of them were destroyed. So like a glacier came through this valley and it got rid of all the rock in between. So there were puzzle pieces, really important ones in there, that are gone, or they're underneath the Chilkat River and we can't really get to them, or they're under the soil and trees and we can't get to them very easy, or they're like in the mountaintops where we haven't had a geologist walk everywhere here. And so we are missing lots of puzzle pieces, but through time we will get more puzzle pieces. We'll be able to make it, our story or our picture, clearer and more accurate. Okay, so I'm gonna go through one little puzzle I didn't have time to do last week. And the other reason I mentioned this puzzle analogy is tonight we're doing rocks, and rocks give us some ideas. There's some of the puzzle pieces. Now, some rocks don't tell us very much, like this piece right here, it doesn't tell us very much, or this one down here, but some tell us a lot, like these ones that have both sky and mountain. So some rocks are very, very important puzzle pieces, and that's why it's important to look at the rocks. Okay, so let's go back to something we talked about last week that I didn't have time to talk. So this is a cross section through Mount Riley. So there's Lynn Canal over here. Hopefully you guys can see my cursor. I'm sorry, Lynn Canal, and over here is Chilkat River, and this is Mount Riley. And so imagine it's raining and the water rains down, and some of it runs down the hillside in streams down to the ocean, and some soaks into the ground and makes its way down to the water table. So the water table, everything below that imaginary line here, is every little space is filled with water. Above that the spaces may be wet, but they're not filled with water. And in the water table, the water wants to flow downhill. And so it's working its way down towards the ocean. Okay, so that's sort of how groundwater works. Now, this is a map. We have Lynn Canal out here, and we have the Chilkat River over here, and the land is kind of this yellowish greenish color. Here's the Chilkat Peninsula in here. And these bright orange lines are faults. We talked about this last time. These are major, major, major faults, these ones that go up Lynn Canal and the one up Chilkat River. They're basically like the San Andreas and had huge amounts of movement on them long ago. Not very much movement on them anymore. However, they are still faults and they can still move and there can still be earthquakes on them. We had an earthquake a few weeks ago on this one over here down near Glacier Point. So there's also a fault that connects between those two faults right here where my cursor is going, and it goes through Mud Bay and through Letnikoff. And one of the puzzle pieces or the clues is that right here where it's this little oval is that's kind of yellow, there are people who have salt water in their wells. And that is a really big clue, and it means something's going on because these blue lines here are the way the water table is moving underground. So it moves from the top of the hills and it's moving down towards the ocean. And over here you can see water's coming off, this big ridge and going that way too. So there should be fresh water in people's wells in this narrow band in here. There's not. There's salt water, or at least in some people's wells. So why? That's really important. So now look, here's where the cannery is. So I'm going to go back in time on this fault. So this fault, see, I've got these little arrows as to which way the land is moving. Remember, fault is two blocks of land that are moving in different directions and they're rubbing up against each other. So on this side, it's moving to the northwest compared to this side, which is relatively moving to the southeast. Okay, so we're going to go back in time. So imagine that this dot is the cannery, and I don't know how long ago this is. We don't have all the puzzle pieces yet, but I'm pretty sure this is, a story that I've put together. I'm pretty sure this is what happened. I just don't know the timing. So this circle with the blue on the outside, that's where the cannery kind of is in real world, but this is where it was, I don't know, tens of millions of years ago. Okay, so we're just going to kind of go through time moving towards the present. So this piece of land is going to move to the northwest. So now the cannery went and it's back to where it should be. And now you can see where Mud Bay is and Letnikoff. So let me do that one more time. So we're just going to go, let's see, does it go one more? Nope. Okay, so there, and we're going to go towards the present. And so this chunk of land here is just going to keep moving. Okay, so the reason there's salt water in those wells is there's this fault, which we don't really have proof of in any other way. And there's the salt water at Mud Bay is able to travel through the broken rock in that faulty zone where it broke up all the rock, and it can come out here. So salt water is flowing between those two places, and the fresh water that's coming from the mountains underground isn't getting through because there's salt water in there. So that's why people have salt water there, and the salt water is telling us that there is a fault there. Because there's lots of fresh water. It should have been able to keep out the salt water. So you can also see the peninsula takes a jog there, which, it's probably a very resistant bunch of rock. And so the glaciers, left them and took out the stuff in the valleys here, the rivers and Lynn Canal, but left this band of rock, but it's got this kink in it. And that's why, is because that land got shifted. I forgot how many miles this is, and I don't know how long it took to happen, and I don't know if it's still happening. It probably is still moving a little bit, but probably not very much, and I wouldn't think that there would be earthquakes there, but that's why there's salt water there. So anyway, that is a little jigsaw puzzle that we've put together. And so that shows us that even just having salt water in your well can be a really important piece of the data that we use to put together the geologic history. So on this slide, we're not going to read all this, but you could take a picture with your phone or do a print screen with your computer or come back later. But if you have well data on your wells and you're willing to send it to me, I might be able to use it to figure out some other bits of geology. So here's the kind of information that I could use: your name, where you live, how, all the elevation, the flow, what they hit when they were drilling. This would be on your driller's report or whatever information you have, you can send to me. There's my email address up there. Okay, so tonight I'm mostly going to try to talk about what rocks are underneath your house and possibly over your house, again with the landslide situation in mind. I'm going to introduce some terms which I hope will be helpful when we get reports from various consultants over the next few years about landslides. So if you're more familiar with the terms, then it'll be easier for you to follow along and easier for you to ask really good questions of those people. So one thing I really want to make clear is just knowing what kind of rock you have above your house and under your house doesn't really tell you very much about how likely you are to have a landslide. So Beach Road, part of the problem was that it was this ultramafic rock, but that's really just a very small factor. Every place that there's ultramafic rocks, people who live on them don't need to freak out and don't need to be scared. There are all sorts of other things that made that landslide happen. Yes, that particular rock is a little bit more crumbly when exposed to the air, but that's not the whole story. So if you do want to know more about landslides, I wanted to point out that Liz Corneo put together a bunch of information, and it's on a web page, and the address is down here at the bottom. It's on the Hainesboro website, and it has lots of information that related to landslides, including this one that I've got the arrow with the pink pointing to, is a whole landslide handbook put together by the United States Geological Survey. You have to download it, but it has all sorts of information about different kinds of landslides, what the factors, what you might do to mitigate, and there's all these other things, links that Liz Corneo put together. So I would suggest that you go look for that if you're interested in learning more about the landslides. I'm not a landslide expert at all, so I can't really answer very many questions about landslides. Okay, so I'm trying to do this talk and teach about the rocks without bringing in too much terminology, but I am going to have to teach you some things. For example, what is a mineral? A mineral is a naturally occurring inorganic solid with a definite internal structure and a predictable chemical composition. Most rocks are made of minerals. And minerals here's some pictures of various minerals, some pretty ones, amethyst and fool's gold or pyrite and gold, and this is magnetite and diamond. And they have all these really cool properties like the color or what shape the crystals are or how hard it is or how dense it is or things like being magnetic, because the atoms are arranged in certain patterns. And what kind of atoms? So like salt is made of sodium and chlorine, and they're packed in a certain way that gives it the characteristics that it has. So how they're organized and what the atoms are, if they're iron and magnesium or silicon or aluminum, determines the characteristics of the mineral. Now, most rocks are not made of these minerals. They're made of these minerals, or at least the rocks we have in Haines are, these are common minerals in those rocks. So this one over here at the upper left, that's mica, is what you would know it as. If it's black, it's called biotite, and if it's white, it could be called muscovite. There's other terms, but those are the most common. The one in the middle up here is quartz, and this over here, the pinkish one, is feldspar. It's not always pink, but it has a particular shape and it has a particular hardness, and it's very abundant in the Earth's crust. And the one down here in the lower right is hornblende. That's just another very common mineral. So but here's the rock that they are in, this one with the red rim. This is granite. So it's got the pink and the black and the white, but they aren't in these shapes those little bits. And that's because when these minerals grew in this rock, they kind of bumped into each other. So they couldn't end up forming the preferred crystal shape that they would like to have. The picture of the rock with the green around it, the green border, is rhyolite, and it has the exact same minerals as this granite. They're just too small to see. So just because you can't see the minerals doesn't mean that they're not there. So another term you need to understand if you're going to ever be talking to a geologist is crystal. So when you hear the word crystal, you probably think of these pretty amethysts or quartz. But really to a geologist, a crystal is something where the atoms have arranged themselves in a certain way in a mineral, and then it has particular properties. So in this picture of that granite, each one of these things, it's a different color. This pink is a crystal of feldspar, and this black is a crystal of hornblende, and the white is a crystal of quartz. So if I use the word crystal, or some other geologists, they're not thinking these two pictures up the top. It just means that you can see it, and it's one piece of a mineral. So again, here's that granite. You can see the minerals, you can see the crystals. This rhyolite has the same things, but they're too small to see. And this picture down below is a photomicrograph of the rhyolite. So microscopic view. This might not, probably not even a rhyolite, but anyway, when it's very small, there are still crystals in there. Okay, so a few more terms. You probably remember this from 3rd grade maybe, or maybe you had a geology class in high school. So this is the rock cycle, and there's 3 main kinds of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are the ones that form out of magma or lava from molten rock. It cooled into a rock. Sedimentary rocks are rocks that formed near the surface of the earth. So if you had sand on a beach, and the beach got buried underground a couple miles and got heated and squished, it can become sandstone. That's a sedimentary rock. And then metamorphic rocks are rocks that got buried in the earth, and as you go deeper in the earth, it gets hotter and there's more pressure, and they got squished and changed. Metamorphic means change, metamorphosis. So they're rocks that got changed. And the rock cycle means an igneous rock, like a granite, can be cooled to a rock, and then it can be squished and heated up and changed to be a metamorphic rock. And a metamorphic rock can go deeper and deeper and then be melted. And then when that cools, it can be an igneous rock. And igneous rocks and metamorphic rocks can be eroded into sand and gravel and turn into a sedimentary rock, etc. Okay, igneous rocks. We're doing this real quick. So here's a little cartoon of a volcano, and there's a magma chamber under it, different sizes and all these other things. So igneous rocks cooled in one of these places where there's the pink, or it eroded out and erupted out as a lava flow. If it cooled underground, and it means that it cooled probably very slowly, and the crystals have more chance to get bigger. All those atoms of silica and iron had time to move through the magma and attach to some other ones and form a bigger crystal. Versus the rhyolite here, the picture on the right, was from probably a lava flow, and so that cooled much faster. And so the crystals didn't have a chance to get bigger. So the size of the grains tells you something about how fast it cooled most of the time. We'll not talk about those other times tonight. Igneous rocks, they are classified and named based on how big those crystals are and how much iron, magnesium, and silica they have in them. So what they're composed of, what the magma was composed of. So on the top row up there, those are the ones where you can see the crystals. Those are called coarse-grained. So examples of those are granite, which are light colored and sometimes pink, and granodiorite and diorite, which are kind of mixed white and black, and gabbro, which is usually very dark, and ultramafic, which are very rare most of the places on land, but very common in Haines. They're very, very black and dark and big crystals, and they have a lot of magnesium and iron in them. Magnesium and iron makes things dark. Feldspar and silica makes things light. So these, from right to left, changes the composition of the lava or magma. And the lower row are the same compositions as the ones above, but the crystals are very tiny. So they formed in lava flows or in these little things close to the surface where they cooled faster. Here are the ones that are common in Haines. So granites, granite diorites, gabbros, ultramafics, and basalts. Those are the most common. We have the other kinds here too. Haines has a very unusually wide range of types of rocks. As a geologist, it's a great place to be. So one other concept I want to talk to you about, and then we'll go look at your neighborhood and figure out what you have under your house and above your house. So you see that these rocks change by how much feldspar silica and how much iron they have in them, but they're not distinct. It's not like this is an orange and this is an apple. It's more like they grade from one to the other, and that means sometimes it can be very hard to give a name to something. So this is another analogy. So you can see the green in one corner up here and the blue over here. Everyone's you ask is going to say this is blue down here, and it's easy. And up here, everyone's going to say it's green. But what's in the middle, halfway between this and this, well, some of you are going to say it's blue, and some of you are going to say it's green. And if you wanted to be accurate for the colors, you'd have to do a spectrogram, use a spectrogram, and figure out the wavelength, and then you would know by definition. Rocks are like that too. Between granite and diorite, there's the whole continuum of possible rock compositions. And so if you're at one end, it's easy to tell it's granite or a diorite, but in the middle, it's really a bit hard. You could hand me, a geologist, and I may not be able to tell you exactly what its name should be. I may need to send it off to a lab, and they'd have to do a composition or do some other tests, and then I could tell exactly what it is. So when I use terms around here, I'm not so concerned about that. If you can say it's a diorite or diorite or a granite, that's still going to give you a lot of information, even if you can't exactly tell if it's granite, diorite, or diorite. Okay, sedimentary rocks. Here's the common names. Sorry, I'm going through this so fast, but anyway, siltstone, mudstone, shale, sandstone, conglomerate, limestone, and chert. Those are the most common sedimentary rocks, and we have them all here in Haines. So the first ones are based on stuff washing off a mountain into a river and into a basin, the bottom of a lake or an ocean, and getting buried deep into the earth, not too deep, like a couple miles, maybe up to 6 miles, and heated up to 100, 200 degrees Celsius, and then it gets pushed, compressed, and heated, and things happen, and they turn into rocks. And then with plate tectonics, they might have been brought up to the surface so you can see them again. We have over here on Kochu Island, this picture on the right, those are cobbles, and in between is sand and clay. That is called a conglomerate. Siltstones are made of silt. Mudstones can turn into mud, or they can turn into something called shale. Sandstones are made of sand. You've all seen these, even if you didn't know what they were called. And limestone is something, we have marble here, which is made of limestone, or made from limestone. It is when you have an ocean and there's chemical calcium and carbonate in the water, and it precipitates out and settles down to the bottom of a warm ocean and leaves a layer of this limey material that then later can become rock. That's what limestone is. And chert is the same thing, except it's silica that has precipitated out of the ocean where it's dissolved, and it forms layers at the bottom of the ocean, usually a deep ocean, and that makes chert normally. So, and sedimentary rocks often have layers because what's getting washed into a basin may change from sand to mud to gravel or whatever. So there's often kind of layers. So we have some of those in Haines. Here's an example of kind of that process. So this is a picture of the Chilkat River, looking upriver. So you can imagine rocks falling off the mountains and turning into sand eventually, and making it down and being washed down the river. And here the water has moved back and forth through the tides and left these ripple marks. You see those on beaches, even if there's not big tides. If you bury that, this particular place and you bury it at 3-4 miles, heat it up to 100 200 degrees Celsius, you could turn that into rock, and you may be lucky enough to preserve these little ripples. So this picture, this orangish picture, is a rock formed from the same kind of situation. This particular one is Triassic in age, it's a couple 250 million years old, from not in Haines, someplace else. But you can see the little ripples that have been preserved, and it tells us that water was flowing on that particular surface, and people who study this will be able to tell you more than I could. But we have some ripple marks in Haines, and they're on this face of rock here. This is on Delasuga Island. It's not really an island anymore, but near Seduction Point, and this picture is looking towards town, and this is Chilkat State Park, and Twin Coves is off to the left there a little bit. This is kind of David's Cove. Anyway, if you look in just the right light, you can see some ripple marks on this big surface. So those ripple marks are deposited in mud and sand on an ocean bottom, probably not too deep. Water was moving back and forth, and then it got buried deep under the earth with lots and lots of more layers of sand and mud on top. Eventually got brought back up to the surface because of the plate tectonics, and it got turned vertical. So these were formed horizontal, and now they're almost vertical because we have lots of crazy stuff happening with rocks here. Okay, let's look at metamorphic rocks. So they're rocks that have been changed. So an igneous rock or sedimentary rock or another metamorphic rock can be metamorphosed, so changed because of heat and pressure from being deep in the earth. This picture on the right, this lower one, is the rock called diorite. It's salt and pepper. We have lots of varieties of this, white and black. If that got metamorphosed, it could look like this rock above it. And what happened was the minerals got changed from black to slightly greenish. They're a different mineral because it got heated up, and different minerals like those conditions. And the grains got reoriented. See how it's called foliation, but there's kind of this linear feature going through the rock. That is called a metadiorite. Both of these rocks are from Haines and can be found in outcrops and common on the beaches. So the upper one is metamorphic rock, and the one below it was what it originally looked like. Down here on the left is this big greenish boulder. This is from south of, near Battery Point, sort of. It's dark green, it's very fine grained, and there are these light green blebs. This used to be a basalt flow. So it was a lava flow, kind of like the ones in Hawaii. But then that lava flow got buried by lots more lava flows, and it got heated up to almost 400 degrees Celsius, maybe 300 degrees Celsius, and buried, 6 to 10 miles below the earth, somewhere in there, perhaps. Different minerals grew. So instead of the brown or black you'd see in a basalt, this is now greenish. And these little green things also tell us that it's metamorphic, but I don't have time to talk about those tonight. So anyway, this one just changed, the minerals in it changed. That's the main thing that happened. So this other picture is not found in Haines, I'm sorry to say. These big red things are garnets, and these are a metamorphic rock. So sometimes in metamorphic rocks you can have really beautiful things made. This rock used to be mud, and it became a sedimentary rock, and then it got metamorphosed, and the temperatures and pressures were just right, and it had just the right amount of ions, of atoms of iron, magnesium, and aluminum, silica, etc., that the garnets grew really big like this. So this is a metamorphic rock. Not all garnets are metamorphic, but in this one they are. So anyway, that's just another example of a metamorphic rock. So I'm not going to go through this on this picture, but you could take a snapshot, or this talk is being recorded, you could go look another time. But what I've listed here are the rocks that are found in Haines, the igneous, sedimentary, and metamorphic rocks. We do have an extraordinary variety of rocks found in the Haines area. Here are the most common ones. So up here is the metabasalt. That was a basalt flow that got metamorphosed. Up at the top middle, that's a granite. It's white and black, big crystals. Remember, crystals mean that it's one mineral. And it has peach colored, they're flesh colored blebs that are a particular kind of feldspar. The diorites don't have that peach colored mineral, and they usually have a little bit more dark than the granite. But we have different kinds of variety of diorite. We have quartz diorite, which has more quartz, and more granodiorite that has less black stuff. Anyway, if you call all those diorite or granodiorite, that's just fine, but those are very common. Metadiorite are these ones that have been metamorphosed, and then ultramafic are also very, very well, they're common in Haines, very rare most places on land. They often are magnetic, and they're dark green and black, and they have big crystals. We also have a rock called gabbro, but they're really kind of boring, and most people never pick them up. Nobody hardly ever asks me what a gabbro is because it just doesn't look very interesting. But there's a lot of it, and it's usually dark green to black, and the crystals are pretty small. Anyway, okay, so let's go look at your neighborhoods. Let's start at Chilkat Peninsula, then we'll work towards town, and then go to Lutak, and then go up the highway. I hope to get to where everybody lives, and I hope to not put you to sleep. Okay, this is a picture taken from 7 Mile Saddle, looking out towards the Chilkat Peninsula. And so you can see over here, we're going to look at sedimentary rocks first. So nobody has houses down there, but I just thought I would cover it. So Delasuga, Twin Coves, all this part of Chilkat State Park, Cochu Island, and all the way up to about the campground right on the beach at Chilkat State Park. You know, there's a few campsites in there. That's about the edge of where the sedimentary rocks are. This is a geologic map done by Earl Redman in the mid-1980s. And I've colored it, and I've added a few faults. I've colored the sedimentary rocks in brown. So you can see Delasuga area, a little bit in David's Cove, all this part of Chilkat State Park, up just sort of near the boat harbor, and then Cochu Island. That's the sedimentary rocks. Okay, you can see that here. Here's a picture of some of those sedimentary rocks. Sedimentary rocks often have layers. This is, I took this years ago, somewhere between Twin Coves and, I can't remember exactly which cove it was on. I think it's after the second one. Anyway, it's layered. These used to be muds and sands and things like that. Here's one, the little bit of land past the boat harbor. You can see there's layers and they're sticking out. There's some kind of cool stuff around in this particular, actually very spectacular stuff to geologists. And then this boulder my daughter is sitting on, that doesn't belong here. If you came to the last talk, you know this is a glacial erratic. It was dropped by the glaciers. This is actually called a gneiss, spelled G-N-E-I-S-S. We're not going to really talk about that tonight. And here's some of the swirly things that you see on that part of land at Chilkat State Park, up past the boat harbor dock or boat ramp. Very cool stuff, but it's mostly sand and mud. And Cochu Island has these cobbles, and this is called a conglomerate. Very, very spectacular conglomerate. What that tells us is if you go over to Anchorage Point across near Pyramid Harbor, you see something like this in the picture on the right. So you've got all these little rounded rocks that came down the river, and there's mud and sand in between them. If you buried that a few miles and heated it up, you could turn that to rock, and it would look just like what's at Cochu Island. Obviously, they're different in time. So Cochu Island conglomerate was a beach like this, or alluvial fan like this, I don't know, tens of millions of years ago or longer. I don't believe there's a date on them. Okay, so that was the sedimentary rocks. Now let's look at this middle part of the peninsula here, which is in the green. Those are metabasalts for the most part. And here is that same map I've zoomed in a little bit. So here's that, the red arrow is pointing to that fault I was showing you earlier where the salt water is along the fault. So Earl Redmond is the first person who mapped that. And then I've added this little fault here. I don't know for sure that it's there, but I suspect it is based on some stuff that's with that pink arrow. So that goes on the east side of Rutzeback and it comes out through Paradise Cove. If you have a house there, I don't think you really need to be worried. It just means that the ground is all broken up underneath your house. Here's what those metabasalts can look like. You've driven by them every day if you live out in Mud Bay. You probably didn't even think about it. They're kind of boring. There's no layers. They just look like this kind of dull, boring gray, green rock. You might have noticed this. This is, if I remember right, near Carr's Cove. This bright, bright green is malachite staining. So that is a copper ore, copper mineral that's kind of leached out of the basalt with groundwater when it was buried deeper in the earth. It's not something we can go mine. It's not enough. Copper deposits to mine have to be gigantic. This is just a little bit, and it's just pretty. But anyway, the rest of this, it's all metabasalt. Here's what samples of metabasalt can look like. Really boring. They're fine grained. You can't really see big crystals. They're greenish, grayish. Sometimes they have little green bright green blebs in them. Nothing terribly remarkable looking. Here's another one. We saw this picture earlier. This is from the east side of the peninsula between the end of Beach Road and Battery Point, if I remember right. It's green, has these bright green blebs, lots of it. That's what that metabasalt can look like. So again, that's all in this area here. Now there are a few other rock types in those areas. So this yellow arrow here, there's some andesite on the beach below the cliffs at Carr's Cove. I'm not really going to have time to talk about that tonight, but there's some. And out here at Viking Cove, there's some diorite, the white and black speckled rock. There's quite a bit on the beach there. And at Battery Point, there's some other things, and I don't really have time to talk about them very much too, but there's hornblende diorite, and I think if I remember right, there's some ultramafic, some cool rocks. But the rest of this, as far as we know, and as far as has been mapped, is metabasalt. And it's pretty strong, but it is very fractured. Let me go back to those. See, it's all broken up. So, you know, things fall off of those glyphs because it's broken up, as you can see here. And it's a bit softer than the diorite, so it tends to, the glaciers eroded it and smoothed it out pretty good. Okay, so now, here's a summary of the other rocks found on the peninsula. You know, if you're interested, you can take a snapshot of this. Okay, let's go now look at the Beach Road neighborhood. So that's right over in here, and mapping shows that it's ultramafic rocks. Here's the contact, or a guess of where the contact is. So here's Beach Road, there's the trailhead there. Here's those big cliffs that, you know, you don't really notice when you're down on the road. And the dashed line is where people have mapped the contact between the ultramafic and the basalts on the other side. But no, there's no one place you can go and put your finger right on that contact. It's buried under forest. And I don't know exactly where it comes out at Carr's Cove. I need to go check. And so the yellow question marks are because we don't know exact. This is approximate. So this is a picture of the Beach Road neighborhood. This is a LiDAR image. They took LiDAR imagery here in 2014 and again in 2020. LiDAR is a very detailed topographic map of an area, and they use special equipment to do it, and it's expensive and it doesn't exist everywhere. But we had it fortunately in 2014, and it was done again after the landslide. And Dennis Geeson did some things to make it easier to see. It's kind of 3D, and he changed the lighting and made it easier to see the stuff. And here's where the slide is in blue, and here's the road there. So according to the maps, this is all ultramafic. And let's look at what ultramafic looks like. So this is one piece of ultramafic. This grayish, dark gray, lead-like looking mineral is actually magnetite. So here's a magnet sticking to it. And the rest of it is just kind of green. And you can see there's little bits it's changing color. So those are actually crystals. Here's one. This is actually from Mount Riley Road. This is a giant mica crystal. Very unusual in this kind of rock. Very, very unusual. But it's pretty spectacular, and it's very black and shiny. And these other minerals in here are a mineral called pyroxene. Very boring looking, but they're green. And these are amphibals or hornblende. If you could see this, the picture, it's hard to take a picture of rocks sometimes, but it's very shiny, very black. Here is some pictures of the slide that John Norton took. So you can see all these rocks are very green. They're all the ultramafics, but there's also these white rocks, which are diorite. Now, sometimes there's diorite laying around because the glaciers dropped it. But after the landslide, Michael Police went walking around the neighborhood. He lives out there past the slide, and he was doing a little research for me, and he was curious and went and looked, and he found some outcrops of diorite, like this picture here, which nobody knew we had in the neighborhood. I should be embarrassed. I live in the neighborhood, or had lived in the neighborhood, but I had never gone climbing up the hillside looking at what was up there. So here's again the neighborhood, but I've added some things. So I think the diorite, you'd see these kind of humps in the topography there. Diorite's a little harder, and so I suspect if somebody went and walked through the forest and dug holes through the soil and trees and could find that, I would guess that those bits are diorite. I don't know, but we definitely know we have some big sections of diorite that we did not know we had before. Diorite breaks up, it fractures, but it's pretty tough stuff. So it tends to stick up higher than surrounding rocks. The rest of this is pretty much ultramafics. If you walk the beach, that's all ultramafics all along, except where there's no rocks, like there had been no rocks here and here on the beaches. So the slide happened in ultramafic rocks, and it scooped into the bedrock, which is not all that common for landslides. Usually it's just the soil and the trees and vegetation on top. But this cut down into the bedrock. They know that the bedrock, we now know that it was very crumbly. The ultramafic has those big crystals, and when it gets a little damp from rain or whatever, that water can get between the crystals, and when it freezes, it can kind of push them apart. It's just easier to weather large crystals than when they're very tiny in some cases. And so the rock is probably, that exposed, was crumbly. I also suspect that there's a fault in there, and that's what I've drawn in this orange line. I don't have very good evidence, but the LiDAR actually now shows that there's like a little line going through that could be a fault. I suspected because there wasn't outcrop on the beach, so I thought it was a fault zone. The state geologists also now think that maybe there was a fault there, and that broke up the rock, so that would have made it easier for a landslide to grab more material and move it because it was looser. But we don't know for sure. And it certainly was not the only factor. So there was a broken up rock because of a fault, maybe, and we know the rock was weathered, so it was more crumbly, and there were definitely some other things happening, and also all the rain. So anyway, there's some reasons why that fault, or why that slide happened there. One other quick thing I'll say about this neighborhood, over here in this yellow are these weird lines. I mentioned this at that last talk. These lines shown by the LiDAR are slight changes in elevation, and they're little benches cut by waves when sea level was higher. So if you walk into that neighborhood, you never noticed it. I mean, this is right at the beginning of the Battery Point Trail, goes right through there. You would never have noticed, but because the LiDAR picks up all this detail, you can see these benches. And I asked John Norton, who knew Jim Bechtel, and he works for the USDA, and he's the expert at this stuff, and he was able to calculate that the top of it was 12,450 years before present is when the beach cut those at the top, made those little benches. You see, you know, the beaches, the sand gets moved around by the waves and it makes these little benches. Anyway, so we know there was no landslide in that part of the neighborhood, at least for that long, because those benches are still there. Those just very subtle topographic changes. Anyway, so that's what we know about the Beach Road neighborhood now, and hopefully the experts will figure out more causes for the landslide and tell us more. So under the houses and above the houses, it's mostly ultramafic, but there may be large sections of diorite. Boulders got left by glaciers that are laying on the ground. There's boulders and debris that came down from the landslides over the years because the glaciers made really steep cliffs. And in some places at below 350 feet, if you dig into the soil, you'll come across this blue clay, or marine clay under the soil. On my property, I have property out Beach Road in the red zone of the landslide. That blue clay is a couple inches thick, and that was left when the ocean was higher and it was underwater, and the clay made a little layer on the bottom of the ocean floor. And then sea level drop, or the land came up. It's a very complicated story. You have to go to the talk last week. But anyway, some places there's blue clay. Okay, so let's go to town. So the maps map all of town as being ultramafic. But what you can see now on the surface, this part is ultramafic and this part. And where it's yellow, that is where the bedrock was scraped away by the glaciers. So you can't go out in your yard and dig a hole and reach ultramafic rock. It's really far down because the glaciers scraped it out. And one of the reasons they were able to scrape so much out there is there may be a fault in there. This was mapped by Earl Redman in the mid-80s. I didn't have time to figure out what kind of evidence he had. It's certainly believable, but I don't know where that fault is. Don't be freaked out if you have a house right here, because you know I don't even know that it's there, that it's right there, and it doesn't mean there's big earthquakes on it. But faults do break up the rock, and then it is easier to erode that rock away by glaciers and streams. So a glacier came through, and so here's a picture of a glacial area now, and you can imagine Haines was this part in the red circle. So the glaciers covered over town thousands of feet and scraped out rock and carried it away. And then the glaciers were so thick they pushed the Earth's crust down. And so when the glaciers melted, the land came up, but sea level came up too. And so we have a lot of downtown Haines was under seawater at some point in time. This is another LiDAR. I showed this one last week as well. So White Rock Nursery is over here, and here is Mud Bay Road. This LiDAR shows the human features as well. And there's the end of the road, and the sledding hill is over here. But you see these kind of lines. These are old beaches where the waves cut these little ridges into the sand. So we know that, and this is about 350 feet. So we know that everything in town that is below 350 feet elevation now used to be underwater and may have sand and gravel and clay. This is a map that Jim Bechtel made, and it's color-coded based on elevation. So everything that's under orange or in orange and below all used to be underwater. So Highland Estates was out, it was never underwater, and the cliffs and parts way up above Beach Road. So other places, first there's stuff that when the glacier melted, it left a bunch of gravel and sand and mud, and sea level came up and put in some clay as well. And so everything in there, when you dig down, you're not going to hit bedrock. You're going to hit, so let me go back to that. You're going to hit gravel and sand and mud and clay. And bedrock is much deeper, and the bedrock is probably ultramafic. Okay, So in 2012 and this year, right over here, so here's Blue Tech Road and there's Front Street, there was that slump. And it has a pretty thick layer of clay there. It's not that thick everywhere else, but in that particular place, it is very thick. And I don't really have time to, and I don't know very much why it was like that. Here are some pictures from 2012, from that first time that slid. So everything within there was slumped a little bit. Here's what that crack looked like in 2012. This is Ocean View Street. And here's what that crack looked like. So basically underneath this dirt and land, there's a layer of clay, and the clay was pretty thick, and it rained a lot in 2012 and it rained a lot this year. That clay layer got wet. It basically turned to soup. And so everything above it just started to drift and move a little bit. So that clay layer was really important for that particular landslide situation. Whoops, right there. Okay. Whew, covering a lot. Hopefully I haven't put you to sleep yet. Okay, so let's go and look at what's above town, in the cliffs above town. So we just looked at all the stuff that's in yellow. This is a geologic map. It's color-coded by rock types, and yellows usually mean sand and gravel and not solid rock. So this is a map by George Garrels and Henry Berg. Dark purple means that ultramafic, and the light purple means granodiorite and a few other things. It's not a very detailed map. They did a map of the entire Southeast Alaska, and that's just, they just approximated things. They didn't have much time in this particular area. We don't have very good geologic maps of this area. But one thing to note is this line right here, separating the ultramafics to this basalt, kind of in the gray. Here's a map. Oops, sorry, that slide got messed up. Anyway, this black line is that fault. It's called the Johnson Creek Fault. It comes up from Johnson Creek. If you're driving around Lutak, you'll come to the creek. It doesn't have a name on the road or anything. It's where the deep forest is, and it goes up and comes down and goes right down through the saddle and down into Southeast Road Builders Quarry. So that's a pretty big fault, actually. And just town side of that is an area intruded by hornblende diorite. So there's ultramafic, and then there's diorites. Okay, so this is an aerial photo of town, and the yellow dotted line is, I just kind of sketched in. So everything town side of that was under ocean water at some point. So there could be sand and gravel and maybe some clay. Above that was the ocean never got to, and there's not much glacial debris. So it's mostly solid rock or bedrock. You can see the quarries here. There are those light colored areas, and then above it is this kind of grayish bit. Those are the cliffs you see over town. I think they're diorite. I've been up there, but I didn't actually look at the rocks. They're that color just because it's been weathered, but it's the same, I believe, as these quarries that are diorites. We know there's diorite in there. And see, there's no lines in between because no one's done any mapping. And then over here at Highland Estates, that is mostly ultramafic, like on Beach Road, but it has some little veins and dikes of hornblende diorite. So this diorite intruded it, and I'll show you some pictures. And then over here is probably ultramafic, but and definitely it is where it comes back out to the highway. And this red line is the trail. This is Dennis Geeson used his GPS and made that trail. So here that is in more detail. So there's the quarries, and here's the cliff. And you can see some of the houses here. Here's what that diorite can look like. Sometimes you see these little black blebs. So the diorite was a magma chamber that solidified through time. And here it was about 100 million years old, a little bit older perhaps, but not very much. And rocks from on top of the magma chamber could fall in and they'd start to melt, but these ones didn't melt all the way, which is kind of fuzzy edges. They're darker. So those are rocks that fell into the magma chamber and didn't melt. This is a picture over near, I think it's called Hooligan Point, past the airport, go around that curve towards Southeast Road Builders. The black is that ultramafic like you see at Beach Road neighborhood. It's like this up at Highland Estates, but here it's been intruded by these white veins, so some diorite, some lava, or magma, intruded and cut through all the little fractures. And if you took a piece off that outcrop and rolled it around in a river and carried it by a glacier, you could drop a rock just like this somewhere on the beaches around Haines. So that's what it looks like when it's been eroded and rounded. And you can see the edges for the black are very sharp. So those those rocks did not start melting because this was close to the surface and the magma that came in didn't have enough heat to start melting it. But this one was in a magma chamber, so it started to melt the dark bits. This isn't all that important in terms of rocks over your house, but I know you see all these rocks and now you know how they formed. One of the other things that you see in that area is this pink mineral, very, very bright pink. So this is a little dike, it's called, that diorite-ish stuff intruded into all the little fractures in the ultramafic, which is this black stuff down here, and it happens to have, in some places, this pink mineral. Previous workers have identified this as thulite, Thulite. I don't know. You can't really, you'd have to use do some tests, and I'm not positive that anyone has ever done that. I've seen people identify it as thulite, but I don't know that they did all the tests. Here's another bit from around, this is below Highland Estates. These are crystals of hornblende. This was again magma. It has the pink mineral and this. So you see these, and that's called a hornblende diorite because the black mineral is hornblende. Okay, so under houses in town, it's mostly glacial outwash after the glaciers left. The water melted, carried all the stuff from the glaciers, deposited gravel, sand, and clay. And then the ocean came up relative to the land, and a layer of marine clay was deposited on that. Someplace very thick, someplace not very thick. And of course, around town, the land's been moved around a lot. So you may have originally had marine clay under your house if you live in town, but through gardening and people putting in driveways and moving things around, that make the marine clay may not be there anymore. And up above the cliffs over town, it's mostly diorite and ultramafics. So the diorite is very strong, but it's very fractured. You shouldn't necessarily feel safe under a diorite cliff. Okay, now, hope I haven't put more of you to sleep. Let's go up Lutek Road. Here's the geologic map that we have, not very detailed. So here's town again, and there's the road going out. Here's a little bit more detailed map done by Earl Redman and Rutherford and Hickok in the 80s. It's not colored. There's some faults and contacts. So I've kind of combined that information into a map on an aerial photo. So let's look at that. So that Johnson Creek Fault is this orange line right here. The red line is the Rapinski Trail again, and then 7 Mile Saddle. That's from Dennis Geeson. And there's this fault in town that's off Earl Redman's map. And then this big orange dashed line out here in Lynn Canal going up Lutek Inlet is a major, major, major fault. It's basically like the San Andreas Fault, but it no longer has that much movement. But it was a huge, huge fault at one time. And parts of it splay off and go right along the road. This is where Earl Redman is putting the faults. And there's a fault that he mapped in here as well. So if you start in town, you start driving out towards the ferry terminal, you're going to go through this section, which is ultramafics, intruded by lots of that hornblende diorite with the little pink mineral, very messed up looking. You come across and then you hit Johnson Creek, and then you kind of lose all the outcrop. You have a different kind of rock. It's not as strong. So mostly ultramafics and diorites here. And then in here, it's been mapped as metabasalt. There aren't really any outcrops, but other people have probably walked up in here and figured that out. Then you cross another little fault, and then there's Tanini Point, and it's diorite. There's a sample from there that's been dated at 83 million years old. And as you keep going around the road, it's still diorite, and then you come behind the ferry, and there's those cliffs that are very unstable looking. There's faults in there, and it's messed up the rock, and it's probably metabasalt, but it's all messed up. And as you keep going out the inlet, there's more metabasalts and diorites, that kind of thing. Again, the metabasalts look like this. The diorites can look like this, or they can be more boring looking. And then there's the ultramafics that can sometimes look like this, or there's those ones that have the pink metal too. Okay, next section. Let's look at Lutak Spur Road. Aerial photograph. The houses are all in this right up in here. There's some big faults go up through there. Here's where Earl Redmond put them in orange. Of course, we don't really know exactly where they are because the evidence for them is buried way down deep. And this is all debris on top. There's no solid bedrock in this area. So it's just a bit of a guess. But one thing, when they made the map and guessed where those faults went, they did not have very good aerial photos. That was in the mid-80s. There is sort of this linear feature right here on the edge. I suspect that is one of those faults. It's the edge of a cliff, and then all the lighter stuff, I mean, lower elevation stuff, but we don't really know. Anyway, I've put it in there, and there's another little one for sure right in here, and there's several little sprays, but we don't know exactly. Because these faults broke up the ground in this whole zone, when the glaciers were advancing through here, they came through there because it's much easier to erode through broken rock than solid rock. So it scooped out this long, deep valley. Then the glacier retreated. And when it got here, I believe it kind of slowed down in its melting, and it stayed in that spot for a long time, and rocks that fell on the glacier moved down with the ice. And at the front of the glacier, they fell off and made a big pile. This is called a terminal moraine. Here's one, a man is sitting. The glacier was much higher when this rock pile formed. And over in here, if you want to learn more, go to last week's talk. Anyway, I think this whole wide area is one big terminal moraine. So the glacier just dumped huge amounts of material, filling in the valley. So it's now higher than the ocean and the lake. And then the glacier retreated further and further, lots of water coming off the front of it. Sea level is rising because the glaciers are melting. And I think lots of more material washed down on top of this, sands and stuff, and made layers of sand in here. This is a picture that, sorry, I didn't put the label on here. John Norton took this picture after the slides in December. He went up behind the houses and got this picture. So this is loose sand. This was deposited by streams, probably washing out from the glacier. There's a few rocks those are gloves, a few rocks in there, but mostly sand. And then sea level came up, and that sand was reworked by waves on beaches. So this was all underwater in here, and you see these long lines. This is LiDAR again, and this is from 2020, and I don't have a very detailed picture of it. It's a screenshot. Anyway, you can see these lines, and those lines were made by beaches, making just slight changes in elevation. That's what those represent. So we know this was underwater, and that sand was reworked by these lines. There's a lot of loose sand, and so as soon as you got enough water, you wiped out the trees, and the sand just came pouring down into some of the houses. Sand doesn't have much strength. Get it wet, it's going to move. The other thing to be aware of is, see this line on the LiDAR here? Well, it's a fault. I'm pretty sure. And so I've put this orange dashed line. I didn't put it right over it so you can still see what it is, but you can see that the beach lines don't cross exactly. And these beach lines were, I don't know exactly, somebody can figure it out, but probably 10, 11,000 years old, somewhere in there, maybe a little bit younger. So this fault cuts through those, so that there was movement on a fault here sometime in the last 10,000 years. And you can see the land, the landslide materials come across too. It seems like that landslide off the hill over here has been offset. So it's not that long ago that this happened, sometime in the last 10,000 years. Over here is this big valley. I don't know why that's there. It's kind of odd, but those beach lines seem to end there. There may be another fault through there. I don't necessarily know that there's any movement. I don't really know if it's there, but it's a possibility. So here's what we can say. The houses are built in a fault zone. The fault zone was a major, major fault zone tens and tens of millions of years ago. I don't know exactly, exact dates. There has been some, probably some minor movement on those faults within the last few million years. And there's been at least some movement in the last 10,000 years on that that one little bit right over there. So these people have their houses on a fault that at one time was equivalent to the San Andreas Fault. It is no longer equivalent to the San Andreas Fault, but it is still a break in the earth and it can jiggle sometimes. Under the houses and in the hill slopes behind the houses, there's probably no solid rock for hundreds of feet below sea level because the glacier scooped them out. Glacial till, which is stuff left underneath the glacier, and glacial outwash, debris washed out from the glacier, and maybe some landslide debris off the sides of the mountains have filled the area behind those houses. And then on top of that, there's some sand and silt from streams after the glacier was moving back. And then it was reworked by ocean waves and formed these subtle benches, leaving layers of just pure sand and other things. And so that's why it's going to be prone to that kind of landslide that we saw in December. Vegetation can keep that in control some bit. Now that some of the vegetation is removed, it's probably going to be more likely that there's still going to be in places sand washing down at even smaller storms. But definitely, you get big rainstorms like that. This is there's going to be more things like what happened in December. I don't know how often. Okay, let's move up the Haines Highway. I'm sorry I've been talking so long. I'm almost to the end. Okay. So here's that Johnson Creek Fault. We're back looking at an aerial photo of town. You can see it comes right through Southeast Road Builders. We don't know very much about that fault, but definitely different rock types on either side. And if you continue it out, that you can draw a line straight from there all the way, and it just goes right up the Taquin Valley. Now, I don't know that there's a fault there, but it is very suspicious that that valley is there. It's different oriented than a lot of other valleys. And it's I don't think it's just a coincidence it lines up right with that fault, Johnson Creek Fault. And it's probably newer than the Denali Fault Zone, which runs up Chilkat River, because that had major movement and that would have been offset. And if it's been offset, it's not by much. So movement on that fault, if there is one there, was after most of the movement in the Denali Fault Zone. In the Southeast Road Builders, that's metabasalt, just like we had over lots of Chilkat Peninsula. And above that, we have granodiorites and I think some ultramafics as well. I don't really have a map of that, and I haven't spent that much time there. Okay, so let's now continue up the highway. The highway is going along mostly metabasalts along the highway, and then we get to the 19-mile slide right here. I don't know whose picture this is, sorry if I stole it. I think it came off Facebook. But anyway, you can see, what happens there fairly frequently. Big rains, it washes material down over the road. That's been happening a very, very long time. Here is a LiDAR picture that's been color coded by elevation. I'm sorry, I don't know where I got this. Got it a few years ago off the internet. Anyway, you can see there's this thing here. This is called an alluvial fan. And there's one over here at Cluck 1, 2. And here's where that 19-mile slide happened. So the material right now is coming out of this broken area up here. It's in diorites. I don't know why. It's all fractured in there and more easily eroded. It comes down the canyon and it washes out onto this fan. And at times it's washed over here and over here and over here and over here. So through time, where it's washing out moves. And you'll notice in this area, there's lots of cottonwoods. Cottonwoods are the first thing, or one of the first trees to grow up. And it takes longer for the spruce and hemlock to come in. So if you have a lot of cottonwoods, you may be an area where there's been a lot of material washing through. And so all this area is formed because of basically landslides and streams washing material down. And up above it is the diorite. Okay, so let's go over to the, here's the geologic map of 19 Mile. There's where the slides come out now. And geologic maps are color coded. They use color to tell the different rock types. So there's metabasalt in this darkest, and then there's diorites and gabbros, and they're slightly metamorphosed. So metamorphosed diorites can be in there. And then above it are quartz diorites. So those are igneous. These are slightly metamorphosed, and these are metamorphosed. And then all the yellow are sands and silt and mud left by the glaciers and the streams. And so we don't know what's under them exactly. We'll talk about this other stuff in a bit. And here are those big faults going through there. The big fault, the Denali Fault. It used to be called the Chilkat River Fault. It's called the Denali Fault. So here's like the key. Every geologic map has a key. And so you can look at that and see what it all means. So let's look at Cluck-One real quick. Another big alluvial fan. Towns like down in here. So somebody did a study and they gathered information, did a little geophysics and other things. So this is like if you cut right through Cluck-One, cut straight down through the earth, and here's the Tokshnik Mountains over here. And this is exaggerated. It's not really this steep. So the distance along the bottom is a different scale than the vertical axis. And then over here is Chilkat Lake on the left end where that orange dot is. So you can see where the bedrock is, and on the Chilkat Lake side, it's metamorphic rocks, and then here's the big faults, and then on this side, it's mostly igneous rocks. And you can see through this line here, that's the stuff that's filled in from after the glaciers left. And you can see the line between it is sort of U-shaped. Well, glaciers do that. Here's a picture from someplace else, and it's left a U-shaped valley because glaciers erode on the sides and the bottom, and it makes it U-shaped. So there is that U-shape. Anyway, under Cluck-One, there it's at 200 feet above sea level now, and the glaciers eroded down to minus 600 feet below sea level. So bedrock is 800 feet below Cluck-One. A lot of material has come down off the mountains, and a lot of material left by the glaciers. And after the glaciers left, sea level rose. I had this picture last time. It's from Jim Bechtel. He's figuring out that how high sea level came, and it was about 350 feet. This is where it would have been at 300 feet elevation at 13,000 years ago. So 13,000 years ago, his best guess is water was where it is now at 300 feet elevation. Our land has come up, not anyway, so Cluck-One would have been underwater where this arrow was. Okay, so here's the geologic map. Here was the the fan that 19 miles under, and here's Cluck-One. The fault is immediately underneath the town, the Denali Fault. It is big, but may not have very many movement now, but it does have some movement in other places along it to the south. There have been earthquakes on it. And to the north, way to the north, there have been some very large ones. Above that fan, there is metamorphosed basalt, and then the diorites and gabbros, and then this thing called KP here. This is ultramafic, and it is extremely rich in magnetite here, and it's called Iron Mountain. Magnetite is made of iron. Through time, it has been eroded through there, and lots of it has washed down, and this fan is largely made of debris from that, and it's very magnetic. Your compass won't work in this area. At one point, they had plans on mining this and under the town and into the river to get magnetite, which can get turned into iron ore. That is not going to happen. The land has had the mineral claims have been voided, and it will not happen. But there's lots of magnetite, and it would be the world's largest magnetite placer deposit, placer magnetite. So placer means it's debris that washed off the hill. It's not bedrock. So this is one of the largest is the largest placer magnetite deposit in the world. But it's not going to get mined. Okay, so now let's see. Oh, and here's what that ultramafic can look like, and here's some of the magnetite there. And the magnet sticking to it. Okay, so let me see. Oh, here we go. So under Klukwan, there's glacial outwash from the retreating glacier, leaving sand and gravel, and then the streams filled in and bringing in more sand and gravel. Material has eroded off the hillside and left this big alluvial fan, and it is the largest placer magnetite deposit in the world. Above town, there's a large pluton of magnetite-bearing ultramafic, and there's those other rock types. Haines Highway, 23 miles to the border. Okay, so let's go look at Mosquito Lake. Here's an aerial photo. You can't really see very much. There's not much outcrop in here. And going back to that same map, so at 13,000 years ago, the community of Mosquito Lake was also underwater. Here's the geology map of the area. So here's the red circle where the community is. And you see these different colors. So before we were looking at all sorts of pinks and purples and stuff. The greens are meaning these are metamorphic rocks. The orange is called a gneiss unit, a GNEISS. And this is called amphibolite layers. They're mixed units. There's all sorts of different kinds of rocks in there, but they're metamorphosed. They're older. They're Paleozoic, so they're over 245 million years old, and very different from the ones over here because of this giant fault has moved things around a lot. So I don't really know why there's this break and there's this valley here. It doesn't really look like a fault, but there's something curious happening as to why it's so eroded there, not elsewhere. I don't really have very good pictures of the rocks here because, well, lots of them are under the trees. There's not big outcrops, and I haven't spent much time up there. But here's the code from the geologic map. The blue is marble. So that used to be limestone, and it's been metamorphosed. And the orange is the gneisses, and these are mostly schists. I do have a few pictures. This is a picture of a gneiss. I don't know that it came from that area. I don't think so. But anyway, this is a typical gneiss. Here's an outcrop at 25 Mile. These are schists. In here, somebody's house is up above there. So it's layered and it breaks up easily. It doesn't make giant cliffs. It's pretty crumbly stuff. And here's a picture of some marble. So that picture of the car is right down here along the highway at 25 Mile. And if you lived out at the farm, you're on top of sediments, from glaciers and rivers and stuff. And then the greens here are also schists and slates. Used to be sediments that have been metamorphosed. Okay, so I think that circle is about where 33 Mile is. We're working our way up the highway. So let's look at that area. So there was Mosquito Lake. Now we're on the highway coming across, and you see these greens and blues. So the blues are marbles, and the greens are schists and slates and phyllites, and there may be some graphite in there, various things, and some quartzite, just a whole jumble of things, but they're metamorphosed sediments. There's 33 Mile there. And if you keep on the highway up past 33 Mile, we come up to the border, and there's this big section of marble. Ardell and Diz live up in there amongst the marble. If you drive the highway, you'll see this big cliff that's kind of white. That's all marble. So that used to be limestone. It formed at the bottom of an ocean, and it got metamorphosed and heated up, and it's now marble. Oh, okay. So that is all the different rock types around town. I'm sorry, it's kind of hard to follow all of that. I'll try to do some more talks in the fall, but at least now I hope you know what rocks are under your house and what are over your house. When you hear people talking about them, you'll say, oh, diorite, I have that under my house, or you'll be able to understand and follow things better. And remember, you can go to that website down, the address is here, to get more information on landslides. Oops. And then also, if you have any well data sent to me, you can send it to me via email, and I may be able to figure some things out. Oh, thank you for your patience, everybody. I can answer some questions now.
Thanks very much, Cindy. We have one question in the chat, just to give everybody a chance maybe to think of some others. Can you see that in the chat, or you want me to read it?
Yes, I can see that. So it says, is that a common feature of isthmus that there is a fault? Sometimes. It's, yeah. That I don't know that I can answer that tonight, but ask me again. There's more complicated story for some of those isthmus that I can tell you about.
And if folks want to use the raise hand feature, you can go ahead and do that, and I can see it pop up.
Last week's talk, I think there's a link on the Takshnik Watershed website.
I don't know that I've put the link on the website yet, but we have a YouTube channel. There's actually two of them, an old one and a new one, and you can find it there. And it's on our Facebook page, and I'll get a link to it put up on the website here soon.
But they can go to Facebook and find last week's talk.
Yeah.
Which hopefully wasn't as I'm sorry tonight was so long. There's a lot to cover.
Deborah Schnabel, you have your hand up.
I do. Thank you. Hi, Cindy. Thank you very much. This has been really fun and interesting. And I'm struggling right now with kind of undoing some stuff that I thought that some beliefs that I had, I think from reading Roadside Geology. So I just want to clarify. I had always believed that the Denali Fault separated, the igneous metamorphic from sedimentary. But you just, right there at the end, showed that there was marble on the, what I call the north side of the fault line. So that would indicate that really the fault line isn't really separating tectonic plates. I guess that's my guess.
Okay, so
is that what you're telling me? Why is there marble on the other side of the fault
so
line?
The faults, that fault, Denali Fault, was a crustal scale fault, huge fault, and the stuff on the west has moved hundreds of miles or thousands of miles compared to the stuff on the right side or the east side of the fault. So you could have igneous or metamorphic or sedimentary on both sides, but here in Haines, the stuff on the west side of the fault is much older and has a lot of metamorphosed sediments that make up the marble and the schists and the gneisses, versus what's on the east side is largely igneous rocks and metamorphic rocks of a different age. So the stuff on the east side is, there's some that the basalts are probably, 200, 250 million years old. The igneous rocks are mostly 100. And on the other side, they're mostly Paleozoic sediments. So they're older than 250 million years, but then there's some igneous rocks too. So the type of rock, it defines that they're different groups, but they can both be igneous, metamorphic, and igneous and sedimentary.
Okay, helps. Thank you. And then I have one other follow-up question. So, of course, being of a gold mining family, I'd always been told that gold-bearing rocks were only on that, what you're calling the west side, of the fault. And is that not true that you won't find gold in rocks on the east side?
I think that's primarily true.
Okay.
And it doesn't have anything to do with being on either side of the fault, except that the rocks that were on the west side happen to have a geologic history that allowed gold to concentrate, whereas the ones on the east side had a different geologic history and did not. There may be tiny amounts of gold, but not anything that is going to be a gold deposit, and really hardly anything. But it's just they're two different bits that had their own geologic history, and they've been pushed up next to each other because of that fault.
All right, thank you very much.
So there's another question. Is the USGS professional paper 832 with map available? I can't remember which one that is. Some of them, they are all available online, but the USGS no longer prints maps. So you have to go to Kinko's or someplace and have this giant colored map printed. There are some people in town who have various ones. I have some of those, and you can come Xerox them, but you can get them online for sure.
Ron, you've got your hand up?
Yes.
Yeah, hi, Cindy.
Hi.
You were mentioning how you weren't quite sure the depth of some of the sediments under the town site.
Yes.
And I'm aware there's at least one deep well where the borough has there, and other people may have their own wells, but seems like you get some idea of digging down there and finding out where bedrock is through that.
Yes, so that's why I'd like people to send me their well data. I mean, there is some well data out there that I could get. I mean, I just didn't have time, but I hope to have time at some point, and I can start putting some of that together better.
Yeah, I can see where that would really help. Great presentation. Thank you.
Dawn, or maybe Art?
Yeah,
Yes.
I have a question. When you say metabasalt, is that like basalt's an igneous rock, right? And then
Yes.
metabasalt is something that's been heated and altered?
Yes, so that was metabasalts are lava flows. I'm simplifying a little bit here. So they're lava flows, and they had a lot of iron and magnesium in them, which makes them dark colored. And so imagine lava flows happening in Hawaii. I mean, they're a little different, but just imagine those flows happening, and you just build up layer and layer and layer and layer of metabasalts. I mean, it's a couple thousand feet thick, and eventually those got buried, and then they're green schist facies, which that means it was heated in a couple hundred degrees Celsius, and it was under a fair bit of pressure. So it was buried. I'm generalizing here, but maybe 10 miles, maybe 6 miles deep, and new minerals grew and replaced the minerals that had been there before. So a metabasalt is a metamorphosed lava flow that had lots of iron in it.
And do the basalts have a high melting point?
Yes. Basalts have the dark minerals tend to go from liquid to solid to form crystals at much higher temperatures than the lighter colored minerals. It's a generalization, but there's, they know this, and they know what temperatures. I can't remember, 1100 degrees, 1500 degrees Celsius, something like that. I should know. I apologize. But yes, basalts are a higher temperature. When they solidify than a rhyolite, for example.
I have one more question. When the basalts subduct into the asthenosphere, do they persist as rocks for a long time because of their high melting point?
So all the rocks are going to be solid until they melt.
That's true.
And so, and the depth at which they melt is different in different places in the crust, how deep you have to go before it's hot enough to melt. But basalts, the minerals in them has to get hotter before they melt than the lighter colored minerals. And that's why, if you remember that picture of the diorite that had those fuzzy black spots in them, I said they were rocks that fell from the roof of the magma chamber into the magma. Those had a lot of iron minerals in them, and they did not melt. If the bits that had fallen in were light colored minerals, they were quartz and like another piece of diorite, it very well may have melted. But the dark bits, the basalt, would have taken longer to melt than, say, a rock full of rhyolite falling into a magma chamber.
It's a
Does that make
beautiful
sense?
rock. In
Yes.
Montana, they got one called the pinto diorite, which is just like you showed me, but with much larger crystals in it.
Uh-huh. Yeah.
Okay, thank you.
Uh-huh.
Yeah, Cindy?
Yes.
Yeah, this is Don Turner Jr.
Hi.
I appreciate your presentation here. This is really interesting. And at some point, you might come up to our pit and take a look around. There's some interesting rocks and stuff and a different variety of stuff just in that area. So
I missed which area were you talking? I missed a bit of what you said. Which area?
yes, in our pit of
Oh, yes.
Fallon Road,
Yes.
if you at some point you might look, because that has got a various rock in there that some of that is like that magma rock that you're talking about that has sharp chunks in them that's been there that didn't get melded and stuff. And there's quite a few rocks there, but I like your presentation and I appreciate what you've done. Thank you.
Thanks. And I'd love to come out and look at your stuff. And one of the rocks in the pictures was actually stolen from your land up atop of Mount Riley Road before you had a house there. Anyway.
Well, that's Mount Riley Road's my son's place.
Oh, okay. Sorry. Yeah. Anyway, before there was a house that is very, very spectacular rock, giant biotite crystals.
Well, then where Donnie's is, there was what I called mica. When we drilled that, there was a bunch of black mica in there when we shot that where his house is at.
Yeah. Yeah. It's spectacular. And it's extremely unusual to be found in that kind of rock.
So, thank you.
Uh-huh.
Cindy, this is Derek. I have a question for you.
Yes.
So the well at the Mosquito Lake School, when they first drilled it, it came up with a lot of black. What I've been told when it was tested, it was magnesium in the water, and they've had issues over the years, which I think have largely gone away now. But would that have been? I don't know how deep the well is, but would that have been maybe they were drilling into ultramafic rock that had a lot of iron and magnesium, or could it have been something else?
Well, I don't know. When you say there was lots of magnesium, was it rock dust or it was like a chemical precipitate? I mean, if I don't know, I'd have to. I don't think it was just ground up ultramafic, because otherwise you wouldn't say magnesium, because you can't really look at it and say it's magnesium. So I think there's something. I need to look into it. I don't know.
Right. My understanding was that it was precipitate. Yeah, that came out of the water.
So I don't know why, because I don't know. I've never heard that before. I'm not an expert in that kind of stuff, but I would love to get a little more information and try to figure that out. I don't know. You have to be good at saying I don't know if you want to be a geologist or make up stories. I do both. So feel free to email me with questions or stop me on the street.